Good day, dear Jeff. Welcome back. So we resume our presentation, our course with the theme of fibers on concrete and overlays. Buenos días, Jeff. Reiniciamos entonces nuestro curso con el tema de fibras en pavimentos de hormigón y recapados. Nuevamente darte la bienvenida más cordial. Y iniciamos con el curso. Yo voy a apagar mi cámara para que tú puedas iniciar. So thank you, Jeff. You can start now.
Thank you, Marcelo. And I want to recall our last presentation was primarily on how to go through the design process, planning for types of overlay designs. We did look at some specific design methods, some performance, and now we're going to specifically focus on fibers, as they are one key component to a good performing concrete overlay. And we'll look at the properties we expect for fibers. We'll look at how we would incorporate them in designs that are already available to design engineers. And we'll also look at some theoretical examples of designs using some software and inputting the values for fibers. So we will go ahead, and as you can see, we're talking about in this presentation about fibers that add structural capacity to the concrete, and the picture on the bottom left is highly reinforced with fibers, about 1%. The picture on the right is a X-ray computed tomography looking inside of a concrete beam and showing how the fibers disperse in 3 dimensions. And this is how we enhance the cracking abilities because of fibers' abilities to intersect cracks that are propagating that aren't visible to your eye. So our presentation objectives for this particular part of our talk will primarily deal with reinforced concrete with fibers. Now there's some new updates that I wanted to share with the engineers. These are new resources that have been developed specifically because of questions that have been asked me over the last 10 years. They tend to have pavement engineers tend to have the very similar questions. So we decided, with the help of the National Concrete Pavement Center in Iowa State, that we would write a technical overview, very short, which is the second publication that gives pavement engineers some background on fibers, how to design with fibers, as well as how to specify fibers, and that's only 8 pages. The full overview that gives much more detail on testing, on past projects, on specifications, changes in construction and maintenance. It's 100 pages, and that is what we originally wrote, and then we summarized into 8 pages. And then finally, engineers always ask, well, how much fiber should I add? And so we tried to answer that question with this simple residual strength software that's in Excel. It's essentially empirically based on experience and testing of what residual strength you should use for different types of overlays. And we'll demonstrate that as well after this presentation. The first is that report I talked about. It's 100 pages. You can see the table of contents here. And really, it's I think a good summary, and you can read different chapters to understand specifically how fibers have been used for pavements and overlays. It's not focused so much on other applications. We did write a summary report for use of fibers on bridge decks. That is a separate table, separate report, as well as a technical brief. You can find that also at this same website, cptechcenter.org publications. This is shows you the technical brief or technical summary. That's only 8 pages, so this can be a very easy read in English of some basics you need to know about fiber reinforced concrete pavement design, as well as for overlays. So let's go ahead and start and review some real basics. There are many fibers that are available to reinforce concrete for many different applications. And one question that a lot of engineers ask are, what's the best fiber type? And that question really doesn't have a single answer. Fibers can perform with many different shapes, many different materials, many different types of volume fractions. So the question really is, well, what's sufficient amount of dosage of fibers for a particular application that achieves my engineering design objective? So one could use steel fibers for that, synthetic fibers, even glass fibers can be used. And in some cases, if you're in more of a tropical climate like Brazil, natural fibers have proven to be very successful, as well as even in the US, they use certain natural fibers for thin construction materials, such as fiberboard. So use of fibers really depend on application, availability, costs, and so the decision should lie with the engineers and the contractor who will use a particular fiber to meet the design objectives. Typically in pavements, we've seen primarily steel and synthetic, and obviously economic decision making always plays a role in how much fibers we add. For example, if we're adding steel fibers, we may be specifying 30 kilos per meter cube for a design, and that's been used. Some of the original work was much higher dosage, closer to 1%. And if we're using a synthetic polypropylene fiber, we may specify for a certain overlay type or design 4 kilos per meters cubed. And we may have a performance parameter, which we'll talk a lot about, which is called residual strength, or F150. And we would specify that at 1 megapascal. And that 1 megapascal correlates to some volume fraction of a particular fiber, but not all fibers. So one common statement I like to say is all fibers are not created equal. Just like man is created equal by God, all fibers are not created equal. So we have to add different amounts of fibers to achieve that same residual strength performance. In this picture, you can see macro fibers, and we're really talking about these larger 5 centimeter to 6 centimeter fibers. We're really not talking about fibers that are in the 12 millimeter or less length. And those fibers will really not add to structural enhancement. They have other functions, but not necessarily to help structural design of the overlays or new concrete pavements. And you can usually typically tell in this picture here, you see the microfibers are the very thin polypropylene, probably around 10 to 12 millimeters, and then the very long 50 millimeter macro fibers. So you'll hear the term macro fiber or microfiber referring to these two distinct fibers. One typically having a much higher modulus value, elastic modulus. The microfibers have very low elastic moduluses. And this gives us some, again, contrast of macro fibers. You can see this is one of the first generations of macro fibers in the lower left-hand corner. And it had its length was about 40 millimeters. And if we did a load test versus deflection, you can see a macro fiber after a peak load, let's say of around 4 kilonewtons for this beam size, 4.5 kilonewtons, it continues to take load after it cracks of up to 1 kilonewton for a very large displacement or opening of that crack. This is a behavior of macro fibers, and most macro fibers will behave in this way. This post-peak, as we call it, increases with the quality of the fiber as well as the amount of the fiber. So if you have very few fibers, your post-peak will be close to 0. If I add, let's say, 2% fibers, my I actually may have no drop in the peak load, and the fiber would kind of harden the concrete such that I achieve even a greater ultimate strength. And some of these systems are now coming into the market commercially, where we have what we call strain hardening fiber reinforced systems. They may make their way into overlays, but they have excessive amounts of fibers, and this is obviously going to be much more costly, but they've typically been used for bridge deck overlays right now. So just another picture of kind of trying to categorize different types of fibers. I haven't talked much about shape. Fiber shape is also important because it can help control the performance without necessarily increasing the volume fraction. So I could make a fiber very smooth such that it's easy to pull out, or I can create a fiber with some texture. And if we want to increase the frictional characteristics between the fiber and the matrix, then we create more texture of the fiber, and it's harder to pull out, and then increases its residual strength performance. And so fiber manufacturers generally know this, and they create these geometries to optimize the effectiveness of their fibers. Generally, microfibers, the very small, low modulus fibers, are straight, and they're primarily used to control plastic shrinkage at early age. So for instance, in Bolivia, at early ages, when you have very low humidity, windy conditions, microfibers can be very beneficial in crack control near the surface. Once the concrete hardens significantly within a couple of days, these microfibers are effectively not helping at all. So a combination of micro and macro can be very beneficial, especially when you have extreme climate conditions, drying shrinkage early, plastic shrinkage early, as well as long-term curling. So a hybrid system of macro and microfibers can be beneficial, and you'll see some manufacturers actually sell these together as one a bag that you can enter into the concrete mix. I wanted to show this graph. This was from a thesis of a student of mine, just to kind of reinforce that not all fibers are created equal. We can have fibers, and this is load versus deflection of this beam. We were just trying to demonstrate that if I have a certain volume fraction of a certain length of fibers, let's say close to 0.5% of a 50 millimeter fiber, if I essentially used a fiber that was half its length, note how much big of a drop I get in the post-peak load carrying capacity. So it drops almost in half by just chopping the fiber in half to 20 millimeters from 50 millimeters. Note a slight change in the fiber length didn't make a huge difference, but a significant change did make a difference. Note the very small microfibers here offer very little resistance, post-peak resistance. And note, when you use smaller, finer fibers, you can't add as much to the mix because they tend to ball up much more rapidly. Given their length to diameter ratio gets very large very quickly. So microfibers, you do never add at the same dosage level as you add macrofibers because of the mixing. So the performance, again, of fibers that are very similar even in their properties, but their lengths are different, can change pretty dramatically the residual strength. So as we kind of think about fibers, I'll kind of tell you what the answers are of how fibers can be used. I'll kind of back these answers up by the end of the presentation, but we'll show in this presentation that fibers do improve the structural capacity of slabs, and that will allow us to reduce the slab thickness or make some other geometric change to the slab to take advantage of the fibers' increased capacity. Fibers will also maintain the uniformity of cracks, crack widths that you have in a section. That can help to maintain load transfer. If you have poor support conditions periodically, fibers can help bridge some of that. It's not a substitution for bad support, but fibers do offer some benefit if you're going to have variable support, especially if you're thinking about overlays where your condition of the existing pavement you can't guarantee always to be highly uniform. Fibers also act to tie contraction joints both longitudinally and transversely, and so it can function like a tie bar. For instance, when you're making short slabs, it serves somewhat as a tie bar between adjacent panels, and that can avoid excessive movement and migration of slabs. And another bonus of fibers or benefit of fibers is reducing the deterioration of cracks. So if we do get a crack, cracks do not deteriorate as rapidly with fibers because of the crack widths are much tighter with fibers, and that can increase the service life of your pavement system. So in overlays, we use fibers for this reason. Anything under 15 centimeters, we anticipate will have some cracking over time, like any pavement. That's how we design them. But the rate of deterioration will be reduced even if you see that crack because of the fibers. And having said all that, we don't want to communicate that in all pavements and all conditions do we need fibers. I think there are economical benefits and structural benefits for certain designs with fibers. In other designs, there might not be that economical benefit. For example, if I'm designing a brand new airport and potentially I have a design, a thick design, let's say of 50 centimeters, I may not find it beneficial economically just to add fibers to reduce the slab thickness. My reduction in slab thickness may be offset by the extra cost of the fibers. So as you get in the relatively thin slabs, let's say 20 centimeters or less, the economical benefits for the reduction in thickness are good, better than the cost of adding the fibers. So when you get really thick pavements, the cost trade-off isn't as beneficial to the owner. It may have some performance benefits, but probably not economical benefits. Historically, as we look back, fibers aren't new. We had a lot of steel fiber projects that were implemented as test case about 50 years ago. These typically used high volume fractions that we don't typically use anymore. These are 1 to 2% volume fractions of fibers, and these typically had very high paste contents or high cement contents. And so although we saw a lot of testing early on and that demonstrated fibers reduced the required slab thickness from some of these full-scale testing, as well as allowed for some increase in the joint spacings, there wasn't much of a mechanistic understanding of why this was happening. It was very experiential, and therefore there wasn't a lot of applications used in design methods for fibers for quite some time. Furthermore, there were engineers based on limited understanding of how fibers were behaving. They began to really over design with fibers by increasing the slab lengths as well as reducing the slab thickness simultaneously. And in certain cases that are documented in the literature where there was high curling with these increased joint spacings and reduced slab thicknesses, there was some premature cracking, as well as there wasn't very much technical literature on how engineers could design with fibers. It was more based on experience, and therefore even in the late 80s and early 90s there wasn't a push to see fibers in regular designs. So you may ask, well, what's changed since those experiences 25, 30, 40 years ago? Really the things that have changed is both in concrete technology and the design and structural testing. of the benefits. And so over the years, we've seen introductions and improvements in additives for concrete mixes that allow easy incorporation of fibers and mixing of fibers, as well as the introduction of synthetic fibers, which are much easier to mix and batch. And we've learned a lot about how to batch fibers such that they don't create these fiber balls, these balls of fibers that stick together. So we've learned a lot about that and how to instruct contractors and engineers how to avoid those things, because they do exist and they still exist, and you just need to figure out how to work through them. So we also found that we don't need 1 or 2% of fibers to see a structural benefit. We can see benefits at 0.5% or less, which is also economical. And then finally, we've now developed codes starting with a design method we did back in 2007, where we could enter fibers into a design code for overlays. This is our IDOT bonded concrete overlay design that's listed here down at the bottom with myself and Borderland. We actually included that in the structural design, and then there were some other design programs. Juan Pablo Covarrubias from Chile incorporated the same methodology in OptiPave, which has been successful, as well as PIT BCOA-ME has incorporated fibers, as well as some floor slab design guidelines for designing commercial floors and indoor rack facilities. So before we get into some of the performance, just as a mechanistic understanding of how fibers work, and this helps you to understand when a fiber may be beneficial and when it may not be. The length of the fiber, as we think of macro fibers, it essentially is related to the tensile strength of that fibers, whether it's steel or synthetic, and this tau, which is a shear strength of the interface between the concrete and the fiber. And then finally, the diameter of the fiber. So we have a relationship between this pull out, and we want to pull out of a fiber. We don't ever want the fiber fracturing in general. So ideally, we want fibers to pull out of the cement matrix. That maximizes the energy dissipation as the concrete begins to crack. The more and more energy is needed to pull the fiber out, and we can then maximize the fiber's benefit to the concrete and the design. So if you can think of the critical fiber length, if we increase the tensile strength of the concrete, that'll allow us to have longer fibers. If we reduce the shear strength between the fiber and the concrete, that will also allow it to pull out, and we can have a longer length. But there is a balance there. So if we get too long of a fiber length, one can imagine the fiber breaks. And if we get too short of a fiber, it doesn't pull out as well. It doesn't dissipate as much energy. We can also have too long of a fiber that causes mixing problems. So if we have, let's say, a 20 millimeter fiber versus a 40 millimeter fiber, we can't go much bigger than 40 to 50 millimeters, because we'll start breaking the fiber, because the bond is so good to the fiber that it fractures the fiber. We don't achieve this pull out behavior that we want. So that's the mechanism that improves fiber. So if you have shorter fibers, 20 or 10 millimeters, you won't achieve residual strengths that are very good unless the concrete strength has changed. So for very high strength concrete, let's say I was going to design a compressive strength of 50, 60 megapascals, I could probably use shorter fibers just because the bonding is much better on a 50, 60 megapascal concrete than it is for a 30 megapascal concrete. And I would probably fracture a long fiber with a high strength mix, but I likely won't with a shorter fiber. So fiber geometry changes with the application, and some fibers were designed for higher strength mixes. So when you go to higher strength mixes, generally you use shorter fibers to avoid fracturing the fiber and not getting the residual strength you want. So let's just look at what people have found over time. There's many studies on this, and it's included in the report that I did, that really for low volume fractions of fibers, less than 1%, you shouldn't expect any change in the flexural or compressive or tensile strength of the concrete by adding fibers. So adding fibers, running your standard lab test, shouldn't change flexure, compression, or tension at all. It will obviously increase the ductility of the concrete. As cracking begins, you'll be able to carry much larger deformations at much higher load levels than with plain concrete. So being that your specifications are built on beam tests or compressive strength tests, how does the fibers affect the design of the slabs in? Because if I'm designing based on flexural strength or compressive strength, I've already concluded that fibers actually don't impact those specific lab test measurements. Okay, so we'll answer that question in a second, but that's a good question that many people get confused about. And the short answer is our standard quality control tests that we typically use for paving do not quantify the benefit of fibers. They quantify the quality of the concrete and whether the quality changes from mix to mix or truck to truck, but it doesn't necessarily talk about the structural benefits of fibers by just running this standard cylinder test. Now, what are some of the things we can expect for the property of the properties of the mix to change, especially in the fresh state, when we add fibers? First of all, really this depends on the mixes that are normally used by a government agency or a contractor. In some mixes, it may not change much of the fresh properties. In other mixes, you may have to make some adjustments. For example, in terms of workability, we may see a reduction in the workability. Fibers obviously have more surface area, so they may reduce the workability of a particular mix without fibers. So that makes sense, assuming you have a reasonable amount of paste in your mix. Now you can counteract this if you do have a workability reduction by adding water reducers, or you could adjust the mix in other ways to increase workability. For example, you could slightly increase the paste volume to be able to coat the fibers a little bit better. You could change the aggregate gradation. That may help a little bit to give you some more void so that the fibers don't affect the workability as much. So there's strategies, and so you shouldn't be surprised if there are slight changes in workability. And in many cases, fibers do not change the air content, but in some cases they do. Again, this depends on the type of fibers and the type of mix. So I'm talking in general here because sometimes mixes are placed by hand, slumps are higher, and you may not see a big change in the fiber content. However, if you're slip forming with zero, very low slump values, then you may see even a bigger change in the workability for slip form paving. And therefore, the effect on air content is really kind of related to the workability of the mix. So some mixes, the fibers may just entrain a little bit more air. If it's a much higher slump mix, such as a 15 centimeter slump mix. So this is just a summary, kind of giving you confidence that adjustments will have to be made, just like you have to make adjustments to a mix. If you add a water reducer, you may need to take out some of the batch water, or you may be able to reduce some of the cement because you have better workability and get the same strength. Likewise with fibers, you may have to make some adjustments. So trial batches are important. Other properties in the fresh state shouldn't be changed. Generally, your unit weight isn't really significantly different, especially with synthetic fibers. As I said before, the strength properties really aren't different for low fraction volume fractions of fibers, but the only time you may see differences if you have some segregation or balling of fibers that occur within a specimen. So you can see a reduction in strength, and that's more about quality control and proper specimen making. In terms of shrinkage of the mix, we don't expect for low volume fraction of fibers to change the free shrinkage of a mix, but we may see it. We definitely see an extension, if you've heard of the ring shrinkage test that's sometimes used to specify cracking resistance of materials, especially for bridge decks. You may see an increase in the time to cracking for a ring shrinkage test. And finally, in terms of hardened properties, we could imagine that fibers for a given level of stress would increase the fatigue life. And we can think about that in terms of we need more and more energy to propagate cracks for the same load level with fibers, which I'll get to in a second with some of the testing we've done. So back to, well, what are the benefits of fibers? I've kind of argued already that they are beneficial, but I haven't demonstrated that they're beneficial. So here's some tests that we did to kind of answer that question. We made 6 different slabs, 1 plain concrete, 2 with different volume fractions of synthetic fibers, and then 2 with 2 steel fibers. Number 4 and number 5 are steel fibers with different volume fraction. And finally, welded wire fabric or steel mesh is number 6. And this is all made out of the same plain concrete material and cast in the same size slabs and then tested on the same type of soil. So we could then, given everything being equal except the reinforcement in the slab, we could determine, does the load capacity of the slab change with the fiber reinforcement or not? And this gives an idea of the types of fiber reinforcement. We were using macro fibers only. These are very high performance metallic fibers in the center. This is a very common synthetic flat fiber of polypropylene, polyethylene, and another wavy fiber here with a lower aspect ratio than the hooked in fiber here. And so we have some very different geometries, different modulus of elasticities. And really one question is, do they actually perform the same? When we ask people if synthetic fibers will do as well as steel, most people will say no, but we'll see what the answer is in a second. So we then loaded these slabs containing these fibers, did a center loaded slab, and this is about a 2.5 meter by 2.5 meter slab. We load this in the middle to make sure that the load is uniform on the subgrade. There's a subgrade under this, a clay subgrade soil. And we then plot a load of those slabs until failure versus the deflection of the slab. And note, this does not look like a beam test. This is a slab test where the plain concrete beam is this kind of bluish black beam here, where the first flexural crack occurs about around 100 kilonewtons. Note, the rest of these curves are for fiber reinforced materials generally, and note where their first cracking load is, it's generally over 125 to 150 kilonewtons at a slightly larger maximum deflection. And we do have multiple cracks that occur on these slabs in different directions. So that's what you see here when you see a big drop off and then an increase and a drop off again, and then a ultimate load out here. So fibrous slabs and plain concrete slabs, they crack in multiple directions. And then you have with fibers an ultimate strength that happens about 12 to 13 millimeters, which is very large. We wouldn't expect that for a pavement, but we can see even the first cracking capacity, which we call the flexural cracking capacity, which is what we design concrete pavements for. You do see an increase in load level, and that means that for the same concrete strength that I would get in a beam, I actually improve the capacity of the slab by just adding fibers. And here's a summary of that. So if I just compare the plain concrete with various synthetic fibers, the ratio here tells me what percent increase in the flexural strength, flexural capacity I achieve. And note, they're not all the same. A lower volume fraction of fibers has slightly lower load capacity than higher volume fraction, and this particular steel fiber at a high volume fraction has a much greater flexural strength, flexural capacity. Note, the ultimate strength kind of follows pretty similar trends to the flexural strength. For floor slabs indoors, interior floor slabs, they typically use this value because that's what structural engineers use in their designs. Pavement engineers typically go with the flexural cracking loads. Note, the tensile loads aren't something you visually see, but these are when cracks initiate, and you can tell with strain gauges when cracks generally initiate. So before you even see a surface crack, which would be what these flexural load capacities are, you would see internal tension cracks beginning to propagate that weren't visible to your eye. These tensile cracks, as you continue to load, propagate to the edge of the slab and the top of the slab, and then this is the ultimate capacity, flexural capacity of the slab. Turns out that beam strengths tend to estimate this tensile capacity here. Flexural capacity of slabs are usually a lot higher than what you would measure out of a beam generally. And if we just compare the percent increases with the various fiber types compared to the plain concrete, you can see these percent increases, somewhere between 25 and 50% increase in strength. Or excuse me, load capacity, increase in load capacity, not necessarily strength. And so the question now becomes, although I'm measuring my properties generally of concrete in the lab with the beam does not show these added benefits that you see with the slab. And so I need some way of connecting the beam test somehow to what I'm demonstrating with the slab tests. And notice the welded wire fabric has a little bit of an increase in capacity with plain concrete, but not a whole lot. And that's a fairly large amount. This is a fairly large amount of steel, welded wire steel fabric in a slab. Obviously, you've got to pay for this, and you've got to have labor to roll that out. So if we know that slabs have a higher capacity with fibers, what can we do about that? Well, we can reduce the slab thickness for the same performance life or same load levels. We can improve the performance of the slab by using the same slab thickness. We can imagine slightly increasing the slab sizes or the geometry of the slabs to offset some added stresses that are going to be generated. And we can also imagine that these fibers give us a longer service life, even if we do get a crack. So we can take different strategies of how we're going to use the fibers in the design method. So let's look. So now I think I've shown, and I'm not the only researcher who's shown that fibers improve the structural capacity. There were some papers published, and it's in that report on this same idea that fibers increase the flexural capacity. But what's going on if we have a microscope and can look at within the concrete, what's going on? Fibers essentially, because of their three-dimensional orientation within the matrix, they can intersect microcracks that form or already are existing in concrete, around aggregates, near aggregates, due to bleed water, due to shrinkage. When you load the concrete, these micro cracks can coalesce or combine to form macro cracks or larger cracks. These larger cracks then can start forming a large macroscopic crack. In all these cases, if you have fibers intersecting these cracks at a very small scale, in order for these cracks to continue to grow and open, you need to open the crack and pull out the fiber. And because we've designed fibers to pull out, it takes extra energy to pull out, and therefore it translates to higher load capacities given the same concrete strength. So to open this crack to a very large width, I need more load to do that relative to the same plain concrete material, because I've got to pull these fibers apart in order to open the crack. And so at some point, we see the crack on the surface, but we still have to add more load in order to see that crack. So that's kind of the process of why fibers actually create a larger slab capacity than you would measure in a beam. Now, a beam is a simply supported test. And what happens is all the energy in this test, which is run pretty quickly, goes to form this macro crack quite rapidly. And so we don't see the behavior that I'm talking about here very easily. It doesn't show up on the beam test, primarily because we're testing it in a simply supported configuration without a support condition like we actually have for slabs. So knowing all this, what can we do with fibers? We can obviously use it to design commercial and industrial floor systems, which we've seen for many years, over 20 years, 25 years. They've been using fibers for indoor facilities to make very thin slabs within commercial floors. And we can also use it for rigid pavement design or concrete pavement design for new construction on various types of roadways, whether it's roads in the city, highways. We've even used it on airports for various applications and overlays. And we've seen a lot more fibers used for concrete overlays, especially on roadways, because it offers economical and structural benefits. So that's what we'll focus on. And a lot of our early work 20 years ago started on overlays to help them be thin and perform well, because we wanted them to last about 15 years. That was our original idea. And one of the big things we saw early on with overlays, you can see this intersection here. This is about a 9-centimeter concrete overlay. Note, you see the panels here are moving relative to the adjacent panels. So this is one problem we saw, is what we called slab migration. And slabs would move relative to adjacent panels and create cracks. It could create roughness. And that was a problem that we actually saw in multiple projects. Here's another project where you can see the slabs here are moving relatively different than the adjacent panels, because the plain concrete of these relatively thin slabs are not heavy enough to keep them in place, and so they move with braking, they move with temperature, and then you have this misalignment of joints that can be problematic and cause distress. So we actually found that by just adding fibers, we really controlled the slab migration or slab movements a lot. And we also found that we could use them successfully on various types of roadway classifications. And I talked about this in my earlier presentation on overlays, that county roads, rural roads, parking lots, some city streets can have steel fibers, synthetic fibers can all be used pretty successfully and have good performance. And as I said, this was one of the earlier test sections we did with bus stops in Chicago, where thinner slabs were used because of the rutting that was going on with the asphalt. And note the fiber content of synthetic fiber content was very high, 4.4 to 5 kilograms, but we had to maintain a very thin slab there because of elevation restrictions in the urban area. And this was a picture of one of the bus stops where you see the rutting due to the buses coming in to the bus pad, and obviously you don't have any rutting in the bus pads. So this is a great application. Definitely will be enhanced with fibers, but obviously with a lot of buses and heavy buses, 10 centimeters of concrete won't last for 30 years either, but it'll definitely outperform asphalt significantly because we really don't have a rutting issue. Here's another example where, again, you can add fibers, build a fairly thin overlay of an existing rural road that would require to be reconstructed, or add a very thick layer of asphalt to get the capacity you need. Here's another rural road that had some nice features. This was an existing road that needed, had some rutting in it, had very little cracking, and essentially we did not mill this road. We cleaned it, and then a paver built the overlay on this about 10 centimeters over the existing asphalt layer. This happens to be a what we call stringless paving machine. You can see the fibers here. This particular design used smaller panel sizes, which we prefer to have basically the 1.8 meter panel sizes, but they used about a 1.2 meter panel size. So anyway, this can still perform pretty well despite the slab space, the joining not being what I would have recommended. And in general, when we look at overlays, particularly with macro fibers, we really see that the joints remain uniform and closed. We don't have these openings with the contraction joints. We do see serviceable cracks, so the cracks don't deteriorate rapidly with thinner concrete pavements, and we don't see slab movements. One thing we do see, though, that we always have questions on is, okay, how do I mix fibers and eliminate fiber balls? And I'll talk about that in a second on the construction side. And we've successfully seen it happen in other countries in Latin America. I know you had a road in the city, La Paz, El Alto, that was a fiber reinforced concrete project that was slip formed. So one project that we got involved in that had fibers recently was a type of isolation joint that they have on airports that's expensive to build. So we use fiber reinforced on an isolation joint. Instead of building this type of joint on the top here or a reinforced joint, we used, we eliminated the reinforcement, used the same slab thickness across this thickened, isolation joint, and we can save money by not having to reinforce the joint or building this thickened edge joint here. So that's one other application on an airport. Some of the O'Hare has also used fiber reinforced slabs for patching on the apron area. It's another application where you have a slab thickness that you must maintain, and you may have heavier aircrafts coming in, and therefore you don't want to take out the base layer, so you use fiber reinforced materials to increase the slab capacity. Okay, so back to, well, now that we've proven that fibers can increase slab capacity, there are so many fibers available, and there's so many different dosage amounts. Manufacturers tell me I only need to have 0.3% or 0.2% to do well. how much do I specify? What's the volume fraction? Should I use straight fibers? Should I use crimped fibers, twisted fibers? Should I use steel? So you have all these questions that you have different opinions on. And so we must somehow, we can tell that different types of fibers and volume fractions of fibers, for instance, this here has almost 0.6% by volume. So it's very high, but this green one here has 0.3%. So it seems too low if I was going to potentially use it relative to this purple one, but this is a much more expensive because I got to add much more. So what value should I be using is really the question. And to do that, we've linked a residual strength test, ASTM 1609, and I believe in 2018 when I visited the lab in La Paz, you had purchased one of these machines to do residual strength testing of FRC beams. And this gives the best connection with the slab test right now and our design methods. So we like to use this because we can connect it to the slab test. We can verify the quality of the fibers based on the residual strength, and it correlates well with what we've seen in the field performance. And so this test essentially measures residual strength of a standard beam that you would use to measure the flexural strength. And this is what the curve would look like ideally. You get a peak load as I load the beam. That's essentially your flexural strength or your modulus of rupture. As you continue to load the beam, it cracks, and then you get this slowly decreasing trend at about 3 millimeters deflection. You then can calculate its residual strength, and essentially that measures the ability to carry load at a certain deformation level. And 3 millimeters is chosen because it allows the fibers to start to pull out and characterizes their pull-out resistance with some deformation levels. And so it's not completely a mechanistic test, but it has a lot of connections to how fibers pull out in a slab. And when we get out to that deflection level, we can then compare different fiber types and their residual strengths, and then determine what its effect would have on the slab. So this value is called F150, or residual strength. We like to use that, and typically we would specify that your fiber reinforced concrete pavement should have a residual strength, or F150, of, let's say, 1 megapascal. And then we just make sure that whatever fiber the contractor is going to use or the agency is going to use, for example, if I go back to this plot here, if I would figure out, if I had a specification that said 1 megapascal, I would calculate what 1 megapascal is in terms of kilonewtons and know that, well, in order to achieve that, I need a certain volume fraction of crimped fibers. If it's a straight fiber, I may need slightly more volume fraction. If it's this high quality twisted fiber, I may need slightly lower. Pardon me. And therefore, different fibers produce different volume fractions for the same residual strength. And here's some tests that I ran originally with the slab test, and you can see that there's 3 fibers that are very similar, and note here this 1 megapascal residual strength is almost achieved by all 4 of the fibers here, a lower volume fraction, a higher volume fraction, and then 2 steel fibers. So if my specification was 1 megapascal, I could basically meet it with let's say 0.35% synthetic, or I could reduce the steel fiber content. Instead of using 0.5%, maybe a 0.4% would work. I'd have to run the test again, but that would be the idea, to allow for different fibers to be used that all achieve the same residual strength. And The residual strength here is in this red column. These are the residual strengths at 3 millimeters. And this is what we would do prior to the project beginning. So we'd want to know from the contractor or whoever is building the road, okay, what fiber type are you going to use, and do you meet the specification that is used in the design? And I'll show the connection with the structural design in a second, but if we need in the structural design to achieve 15-centimeter slab thickness, we need 1 megapascal of residual strength, then the contractor has to prove that that dosage of synthetic fibers can meet 1 megapascal at 3 millimeter deflection. And we did this back in 2010 when I was in Chile. The Ministry of Public Works, they tested a bunch of different fiber manufacturers and produced residual strength. This happens to be residual strength ratio, but you can see the residual strengths are over here, up here on the top, versus fiber dosage. So generally, the residual strength is linearly related to the dosage. So as I add more fibers, I can imagine that the residual strength increases proportionally. And some of these fibers are very similar. Some of these fibers behave differently. And in our state, we just have the manufacturer give us certified tests that they ran for their residual strength values versus dosage. So we know for particular projects what to expect the dosage to be. Okay, so now we have a test method. We know what the slab behavior is. How do we use this in the design? And simply, we have found that the residual strength is a strength parameter that can be combined with the flexural strength of the concrete. With that, we can then use traditional mechanistic empirical pavement design methods, AASHTO or ACPA design methods, to design the thickness of the slab and incorporate the effects of fibers. So in traditional design, we use the flexural strength of the concrete, which I'm calling MOR here. If I modify it to include fibers, I call it the effective flexural strength, and this MOR prime is then used in the design, which includes the effects of fibers. And as you can expect, the effective flexural strength is essentially improving the fatigue life of the fiber reinforced concrete overlay or new concrete pavement, and allowing me to potentially reduce the slab thickness or increase the slab panels. And so here's kind of the simple formulas, which makes it really easy to use. If I'm going to do a design, I'm going to add the plain concrete flexural strength to the residual strength of that fiber. That residual strength of the fiber is seen to be equal to what we would expect for the increase in slab capacity. So if I add that fiber into a slab, I may see a 20% increase in capacity. And that's pretty similar what I would see if I had a 4 megapascal concrete, 1 megapascal residual strength. I see about a 20% increase in the capacity when I add fibers to a plain concrete slab. So for example, here's my 1 megapascal concrete, and if I had a concrete that was 4 megapascals, I actually made a mistake there. So this could be, let's say, the F prime there, or the modulus effective modulus of rupture could be related to the original modulus of rupture plus the 1 megapascal of residual strength. Whoops. And that would be equal to 5 megapascal. This would be a plus here, just so everyone can see it. So this would be the flexural strength of the concrete. That's the residual strength of the FRC, and that's the effective strength you would use for your design. So if you think about fatigue, it's related to the stress ratio, the applied stress to the slab divided by this ratio of concrete strength and fiber residual strength. And so for the same stress levels, your stress ratio goes down and your fatigue life goes up. So I can use a thinner slab or a longer slab, or I can have a larger number of allowable repetitions of a certain truck type. So one thing, so this whole concept was built into this OptiPave program that's done out of Chile. And we tested some of these short slabs about 13 years ago at the university where I work. And one of the test sections was comparing fibers with no fibers for the same thickness and the same load level on the same soil type. And this is our testing configuration. You have about 20 meters of loading here over various short slabs along the edge. And we can compare the time to cracking between fibers and no fibers. And that's shown here at the bottom. So we had this testing of plain concrete and fiber reinforced concrete of about 9 centimeter slabs. And we test about 14 of those slabs with the loading at a fixed loading about 40 kilonewtons wheel load. And we do that until we develop sufficient cracking that we have to stop the test. And this kind of shows some of the performance. So this would be the plain concrete slabs and the FRC slabs, which at about 200,000 cycles, we started having significant failures in the plain concrete slab such that it was very, very damaged. And we continue to load the fiber reinforced slabs way past the plain concrete slabs. And we actually, this is a 9 centimeter slab on a granular base. It's not an overlay. And you can see that we still had slabs that had not cracked when we stopped the tests. And in summary, we see a significant enhancement if we compare the FRC slabs at a certain number of easels versus the plain concrete slabs. And not only that, the time to cracking, but the severity of the crack. So if I look at, here's a crack in a FRC slab, you can barely see it. It's actually right here where my cursor is. But very small. That would consider to be first crack. Whereas if you start looking at the cracks and how they deteriorate in the plain concrete slab, you can see how you have this excessive deformations. And here's some of the deformations you see in the fibers. You can see the fibers, and it holds the cracks much better together over time than you do with the plain concrete slab. So that particular test here that we did with short slabs demonstrated for even very thin slabs on granular basis, fibers, the theory we have on fibers, and we can use this in design. We can prove it in performance. We can prove it in the lab with slab tests, that all this fits together very nicely and can be used for structural design purposes. Another factor that we've recently done here and published just last year was that we added in reinforced concrete slabs, we could really reduce the crack width. So, and this could go for bridge decks or pavements, reinforced pavements, that the crack width with a little fibers are significantly smaller than just regular reinforcements by itself. So the comparison here is reinforced slabs without fibers and reinforced slabs with fibers. And our crack widths are less than 0.2 millimeters, which is really good. So in terms of cracking on reinforced pavements, cracking on bridge decks, this is the real benefit of fibers, is keeping cracks very tight for reinforced concrete structures, pavements, slabs, bridge decks. And we've implemented this for the last more than 10 years in our structural design for overlays that fibers do offer a thickness reduction. So for a given residual strength of fibers, we see a thickness reduction between 2 and 3 centimeters for typical fiber dosage levels. We've talked about this already. So one of the big questions this is the number one question that I always have from engineers and material suppliers is, well, what do I have to change with the mix when I batch it? And typically during the first trial batches of the mix, you'd have these fiber balls that occur because fibers are not dispersing in the trucks or in the batch plant. And so what do I do about that? And so typically when we use 0.5% or less, we can successfully eliminate these fiber balls. And the suggestion and the recommendations to eliminate them really depend on the mix and the mix process, type of fibers, how they're added to the batch plant. And so there's not one way to eliminate fiber balls, but the engineer or the contractor has to be smart and think about what part of their process is creating the fiber balls. So the fibers, it may just need to be mixed longer and more rapidly to not create the fiber balls. You may have too many fibers that are being introduced too quickly, so maybe slow down the rate at which they're added. Some fibers are added in bags, and where you put those bags in the process can create fiber balls. If you add them at the site, it may not be sufficient time to break apart the bags and mix the fibers and get rid of the balling. If you mix them at the batch plant and then put them in a dump truck, you may need a longer mixing time. The mix may be too stiff, and so the bags or the fibers don't mix well enough before they ball. It could be about the sequencing of the mix. How do you charge the mix with the cement, water, aggregates, and fibers? That order will help eliminate fiber balls. And then you may have to add a little bit of a water reducer, and that helps to keep the fibers from interacting too much. So the message here is fiber balls do occur. It doesn't mean it's a bad idea. It means you have to figure out the process to make sure you can mix appropriately and not get the fiber balls, because it is mix dependent as anything is. And small adjustments have to be made in the process. Typically, it's a mixed process, not so much as a bad mix design. What do we have to change with overlays and fibers? Generally, we can slip form fibers, we can place fibers by hand with higher slumps, and manufacturers know that introducing fibers at the plant is probably better. You can add them in the mixer truck, but you just have to mix them longer at a higher rate. But you can expect that fibers can be placed at very, very different workability levels. Your finishing should be fairly similar. Should not use wood trowels to finish. You can still texture with fibers. You may have some fiber hair, which looked like hair on the surface from the finishing, but that'll wear off with traffic and sunlight. And conventional curing is sufficient for FRC fibers. So that shouldn't be any change. So finishing and curing typically follow the same procedures, except the texturing, you have to be careful, especially if you're dealing with steel fibers, that you're going to pull up some of those. So that's why synthetic fibers tend to be used, because they stay embedded much longer. In terms of construction of joints, fibers, the rule here is to obviously cut the joints as soon as possible. With fibers, the joints won't propagate as well because it adds tensile capacity. So earlier you can cut the joints, the better. If you wait too long, then the cracks may not propagate, and so that's a big a thing to keep track of is making sure your notch depths for your cutting operation are deep enough or early enough. It's preferable to be early so that when the concrete is weaker, it propagates the cracks. And one thing with fibers is, of course, for certain traffic levels, you don't need to use dowel bars, but you shouldn't substitute fibers for dowel bars. It's not a replacement for a project that you've designed with good load transfer to use fibers. Fibers have shown to have good load transfer versus time, but really depends on the crack width. So if you have a long jointed concrete pavement with fibers, the joints may open up, and then fibers aren't really that effective. They don't work like a dowel. They're more seen as a tie bar, so you can potentially eliminate some tie bars in contraction joints with fibers, such as with short panels. And really, there's no change in the maintenance with fibers. You can mill a section that has fibers, particularly synthetic fibers. That won't be a problem if you had an IRI problem. And there hasn't been significant amount of faulting associated with joints with fibers to really see a trend at this point. You can have faulting with fibers, but that's more related to the base layer and its erodibility than it is with the fibers. So erosion issues should be dealt with separately. Fibers won't eliminate erosion. They won't eliminate faulting if you have other design issues with your base layer or excessive water into the joints. So as I stated from the beginning, we're going to see that fibers, hopefully you've kind of agree that fibers increase the structural capacity. We can use that to reduce the thickness and offer an economic benefit. It maintains crack width much better than plain concrete. And as we've seen on projects with overlays, it helps with non-uniformity of support. It can also be used to tie joints together, particularly longitudinal joints. And it prevents, for thinner slabs, the migrations or the relative movement between adjacent slabs. It reduces also the rates of deterioration of cracks that do occur, particularly with thinner slabs. So if you have very thin slabs, once they crack, they can become spalling hazards and create large potholes pretty quickly. With fibers, they're held together, and it allows the rate of deterioration to slow down for those particular panels. And so really the next part of this presentation, now that we've seen what fibers can do, general specifications for fibers, how do we more particularly pick what residual strengths that we should be using? And so that'll be our next presentation. We'll get that one up right now.
Thank you very much, Jeff. Everything fine. I think we will be waiting for the questions of our participants when this is ready. And thank you for all the concepts. I think many of the things you have talked today were quite interesting. And as you also mentioned, La Paz El Alto, the autopista, La Paz El Alto, is ready and is working quite properly. It was our first project in fibers, and hopefully we will have some more projects in the near future. Thank you very much, Jeff.
You're welcome. Thank you. Recording, okay.
Good. You are recording now.
So our next part of the presentation is going to just give some general guidelines on a software we developed, particularly to answer questions about what level of residual strength should I use for different pavement designs. We particularly designed this software to answer that question for overlays, but I think the guidelines within the spreadsheet software that I'll show can be used generally for pavements with very similar features and design objectives. But keep that in mind when you use the software and listen to what I'm saying, that the intention was helping pavement engineers design fiber reinforced concrete overlays. So that's what this short slide presentation is going to be about primarily. And this was part of a project that was funded by state highway agencies in the United States in a pooled fund study that we did over the last couple of years, 2018 and 2019. And so knowing a little bit about ASTM 1609, which is the residual strength test, we can then imagine that you can specify the residual strength, but you also have to choose the residual strength such that it's realistic to achieve, as well as achieve the structural design objectives of your particular pavement design. And I give a few examples at the end to kind of show you the idea related to the software plus a design program. But it can be used, the general concept I'm teaching about the residual strength can be used with various design softwares. It can be used with AASHTO, it could be used with the Bolivian software that's available for mechanistic empirical design. It can also be used with OptiPave or an ACPA software as well. So just as a review from our last presentation, this is ASTM 1609-12. -12 has a particular design of these rollers such that it doesn't introduce any in-plane forces in the beam. And this test, as we said, is done on a 15 centimeter square beam. It typically is done between 7 and 28 days. The age of the beam can affect the residual strength because the strength increases with time. As the strength increases, the bond to the fiber increases, and it may break more fibers. So be aware of that. We typically like to do our test 7 to 14 days just because it's quicker, and we get a little bit better characterization without having to wait 28 days for the test. And then recall again that residual strength is what the load level is converted to a stress at 3 millimeters deflection. And that again corresponds to the quality and quantity of fibers that you're using in a particular concrete mix. If you change the concrete mix to something stronger for the same dosage of fibers, you can expect the residual strength to go down. And in some cases, if you have a weak tensile strength of the fiber, it could break significant amounts of the fibers. For example, you'll hear sometimes you'll hear engineers or suppliers say, well, I have carbon fibers, and carbon has a very high tensile strength, which is much greater than polypropylene. And so you expect, oh, carbon fibers should be much better in fiber reinforced concrete. And they may be if they're made with the correct geometry. Typically, carbon fibers are very small diameter, and they'll break at a very low load level. So even though they have a higher modulus, higher tensile strength, they're used at a very kind of like a hair level diameter, and therefore they don't actually work that effectively. They typically ball. And so they have to be designed with the right geometry, right diameter, and the right bonding characteristics in order to be effective. This is just a table that reinforces some of the things we've already been discussing, but it shows different synthetic fibers, 1, 2, and 3, different mix designs and different volume fraction. And over here on the left is the residual strength in megapascals. And you can see that it varies between 0.65 and 1.2, so almost a factor of 2. Of course, some of the differences here are volume fraction changes, or sometimes we fixed the volume fraction and changed the age. Other times we've added steel. Note the steel fiber has the lowest volume fraction and has the highest strength. This is a hooked end fiber. So really, here, Mike, I'm trying to communicate here, not that one fiber is bad versus one fiber is good, that the age that you test the concrete, the type of fiber you're using, or the kind of fiber, specifically its size, its diameter, its length, its surface characteristics has an effect. The quantity of fibers, the volume fraction has an effect, as well as the strength of the particular mix, high strength, low strength, medium strength, which is also related to age. Obviously, if you cure longer, you're going to have a higher strength. So keep that in mind when you're designing your specifications. And if you're trying to interpret data, sometimes if you may be testing at too long of an age and fracturing too many of the fibers, so its residual strength could look pretty not as good as if you tested it at earlier ages. As a kind of review again, and when we're doing our structural designs, remember we're adding the residual strength to the flexural strength, so we achieve this effective flexural strength here with fibers. And the example I show here is if we have a residual strength of our mix with let's say we put in 2.5 kilos per meter cubed of fibers, we achieve a 0.9 megapascal residual strength. We have a flexural strength at 28 days of 4.3 megapascal. Then our effective design modulus of rupture or flexural strength is about 5.2 megapascal. And that would be used in our structural design program, whether it's AASHTO Pavement ME or ACPA's design or the Bolivian design for roads, concrete roads. And then with this information, the fatigue life for the same stress level is adjusted. So that's the general concept. Very simple to implement, tied very good to our testing. It's tied well to lab testing to get the residual strengths. In fact, if you're familiar with the Chilean OptiPave design, this is exactly how they use it in their design, because it was based on our original test with their ideas. So we can use this in many different mechanistic empirical design guides. And really the only thing that's left to talk about is how do we select this residual strength? We could do trial and error and use different dosage amounts, or we could use recommended residual strength depending on the existing condition of the roadway and our design objectives of the new roadway, achieve a certain, specify a certain residual strength, and then determine the quantity of fibers. And we may also want to have enhanced performance, which could relate to how much serviceability that individual cracks have, that they don't deteriorate too rapidly. Or we may want to have very good load transfer across cracks and joints for a very long period of time. So that may increase our desired residual strength values. So that gives the engineer a lot of latitude to select which residual strength to use. So essentially what we're going to do is determine the residual strength so that the engineer can design for the effective flexural strength. And keep it in mind that the primary way to use fiber reinforced materials is to reduce the required thickness of the slab. Increasing excessively the length of the slab, especially when you have high curling, could be a problem. You could increase it a little bit, but To go too far will increase stresses that may not be considered in the design guide you're using. So here's a screenshot of the new software that was done in 2019. And I'll do a quick demonstration of it, but it's fairly simple, and it allows you to look at different types of roadways to do overlays with fiber reinforced concrete. So I'm gonna, the software has several inputs. It asks you for the type of overlay, what traffic levels you're expecting for the new design, what the condition of the existing asphalt is, or it could be, I guess, the base layer or cement treated layer below it. What's the desire for the future overlay in terms of its thickness, even though you don't know that yet? And also what the slab sizes are going to be for the new design, as well as any enhancements or improvements to the performance with fibers that you want. And finally, it'll ask you for what your plain concrete flexural strength should be. And one of the things that when you do an overlay, as we spoke of earlier in the presentation, is how do I rate the quality of the existing roadway? And so there's some guidelines that are published, but they vary. One could measure the stiffness with an FWD, or you could look at the cracking severity and the quantity. But generally, we've kind of categorized poor, fair, and good as a way of trying to keep distinct categories of the quality of the existing roadway. It's fairly subjective and needs engineering judgment, but it essentially ties to the stiffness of the underlying layers. So if we have very poor condition, then the underlying layer stiffnesses will be really be assigned lower modulus values than if they were good, and that way that we can assign appropriately the contribution and the resistance of the applied loads. So that's probably the biggest thing that people try to assess on your site visit is what's the condition of the existing roadway, and how does that link into how much fibers I should potentially use. So if we actually look at the software, I'm going to now share my screen and show the software. So here's our software that I showed. I provided that to Marcelo to share with you, and it's called the residual strength estimator because it's not an exact calculator that tells you exactly what you need, but it estimates what you should recommend to start with in your design. And so the first input of choice is what type of overlay are you going to be designing? If you have a parking lot that you're going to do an overlay, a urban street, another functional class above that is called a collector, arterial, or a highway. It also has one for bus pad. So for instance, if we were going to design a bus pad, for instance, and we would then say, well, what's the expected traffic level for that bus stop? And let's assume that that bus stop was going to have regular buses, but not huge amount of bus traffic. So we could select approximately the number of ESOLs and what's the existing condition of the asphalt. We could list it as fair, some localized poor, or poor throughout. But for instance, if we said poor throughout, meaning it's in bad condition, Note, we give a warning here that you shouldn't be using a bonded overlay. You should be using an unbonded overlay design. If you have a very poor condition throughout the asphalt, it's not going to be good for bonded concrete overlay of asphalt. So let's just use fair here because it suggests that we may have some bond capabilities. Our new thickness, let's say, is between 3 and 4.5 inches, which is basically 8 to 12 centimeters of new concrete thickness. Our remaining asphalt thickness we'd like to keep at somewhere 3 inches or above. Note again, if you say less than 3 inches or 8 centimeters, the program gives you a warning and says you should use unbonded overlay. So it does help the engineer decide what type of overlay you should be designing based on some of the inputs. We desire to have 4-foot joint spacings, or excuse me, 6-foot joint spacings if possible, but we could use 4-foot joint spacings. And it says that, okay, well, we don't use 4-foot unless it's unchannelized traffic, such as parking lots, but you can still design for 4-foot if you like. And we'll just use for desired enhancement, this we'll just leave as basic, and we'll go ahead and use the plain concrete strength. We'll select a value that's approximately, let's say 4 megapascal would be the initial concrete strength. And so based on these inputs, the program recommends that your residual strengths should be approximately 1 megapascal to 1.4 megapascal. And it actually plots a graph here of what the residual strength should look like at 3 millimeters approximately. And note, it gives you an effective flexural strength, which is about 5 megapascals. And that should be what you use in your design program. So this would be your plain concrete strength. This is what you would use in your design program, about 5 megapascals. So, and then you specify about 4 megapascals as your, excuse me, you specify 1 megapascal residual strength as the difference between what you currently have between this value and the 700. So that's about 1 megapascal once you do the conversion. Some of the other features are if you particularly said, well, I've got some, I want to make sure I have reduced crack rate deterioration. So in other words, when cracks begin, I don't want the cracks to deteriorate very rapidly. And it actually increases the recommended residual strength values here to much higher values. It actually doesn't change the design input, but it essentially tells you to add more fibers so that so that you have a reduced crack rate deterioration. So in this case, the recommended minimum residual strength it gives you is approximately, I'm just going to calculate it quick in megapascals. It's going to approximately give you something about 1.2 megapascals to about 1.6 megapascals. So that's what you would specify in your material specification for what the fiber should achieve. Still, in your design, you use the 5 megapascal as your input to the thickness design. So hopefully you kind of see the general idea of how this works. If for instance, I wanted to design a highway or a roadway overlay, let's say on a certain kind of rural road in Bolivia, and I knew generally what the traffic was, and I had an existing asphalt road, and I thought I would get some bonding there, then I could again figure out that, okay, my inputs here would be for the plain concrete is still the same, but for this highway, I'm recommending a slightly lower residual strength value than the previous design because I'm not doing enhanced. work. And the input for your design is slightly less than 5 megapascals. Now you use about 4.7 megapascals for the design input. So there's a lot of options here that you can go through. If you were just doing parking lots, obviously you're not going to have a lot of traffic on parking lots. You can have potentially some thinner asphalt and concrete layers. You could use joint spacings that are smaller because of the variation in the parking lot, and then you could do your design again that's shown here, and your residual strength values are somewhere in this range. So it allows the engineer to choose what level of residual strength to use. So now that gives you some idea of the software, and I did some runs with a couple different cases. This was a bus stop where you're building bus pads like we discussed in Chicago with a certain level of esols. These aren't really heavy buses, but most of the problem with the buses are the stopping and starting. And we're using 1.8 meter slabs with a design flexural strength of about 4.2 megapascals. And we're going to look at what, for a residual strength of about 1 megapascal in the design, we have a range from the software that we just achieved. What is the design thickness that's going to be achieved? That's kind of the example. So I've already run the software, and here's an example of a BCOA ME, which is bonded concrete over asphalt. And if I input those numbers in and use the effective concrete strength that we've been talking about, I end up achieving about the required thickness without fibers is about 13 centimeters. With fibers is about 10 centimeters. So with the residual strength of about 1 megapascal, I'm reducing my required thickness by about 3 centimeters for this bus pad. And if obviously I needed, if I had more traffic, I would have to redesign. If it's much higher than the 100,000 esols, I'd have to redesign it. Here's another example with an arterial highway with a lot more traffic, with an asphalt that has about 3 or 8 centimeters of existing asphalt, with 1.8 meter joints and 4.1 megapascal concrete strength. Again, we'll try to use the thickness design with 1 megapascal residual strength and see what we get for this particular design. And what we see here with fibers, the calculated thickness is about 15 centimeters. With fibers, we have about 11 centimeters. So for this particular design, we used a much higher residual strength than the previous design. We didn't use 1 megapascal. We used slightly larger than that. We used about 1.4 megapascal as the design residual strength. I think I said 1 megapascal, but it's about 1.4. Excuse me, 1.2 megapascal was used for the residual strength. So this design, again, there's some limit to how high a residual strength you want to use. Typically, we don't get into using 2 megapascal residual strength levels. That gets to be very high. We're typically somewhere between 0.9 and probably 1.5 megapascal is the range we would use for residual strengths. And that typically is in the economical region of fibers that we would use. So if we use too many fibers, the economy of the overlay or the design is compromised or gets too expensive, and we may choose just to build a thicker slab than build a thinner slab with fibers. So kind of in summary about the design software, This is a fiber reinforced estimator. It just helps you choose residual strengths, especially for engineers who don't have a good feeling of what the residual strength should be relative to the inputs you're expecting on the existing pavement as well as the new pavement. And it gives you a range of reasonable residual strength that you can achieve with a certain quantity of fibers. And generally it's somewhere between 2 kilograms to 5 kilograms of fibers per meter cubed will give you the residual strength somewhere between 0.9 to 1.5 megapascals residual strength. And those are reasonable values that achieve reasonable reductions in thickness for your design methodologies. Now, after having that, you would write a specification that would include the residual strength value in the specifications, not necessarily the quantity of fibers, unless you had only one source of fibers that you were specifying. But if you didn't care what type or company supplied the fibers, you would just write a residual strength specification that allowed the contractor to use any fiber he wanted or she wanted, as long as they met the residual strength minimum that is specified. Likewise, you may want to add some language related to the types of fibers that are allowed. This ASTM 1116 allows certain types of fibers that aren't going to degrade over time. So that specification makes sure your fibers aren't problematic if they get into a high alkaline environment. And you may have some specifications about max and minimum dosage levels for fibers, also with how significant does the amount of fiber balling have to be before you make a mixed design change. That may be specified just to make sure the contractor knows they have to make adjustments if you start viewing fiber balls in the mix. Okay, so that kind of shows the software, and the final part of the presentation is really related to kind of now putting everything together in a design software that may be applicable to some cases in Chile, in Bolivia. It may be you may use a different software as well, but I'll show the next set of slides here are just some example case studies. Let me actually change this to share my whole screen. And we're going to now show a couple case studies just to understand what to expect for overlays. And I kind of made these up, so they are based on some real projects, but the inputs that I use may achieve a different answer than what was used on the actual projects, because they used a different design software or they didn't use the software at all. So here's a couple things that I'll do the first two now, and then I'll finish up with some ideas on a potential project that you could consider an overlay on La Paz Oruro roadway that is currently being studied. First, we'll look at an overlay that I talked about in the first presentation near where I live, which is a existing concrete road. We'll also talk about one in Chile that was done had an existing asphalt and then did an unbonded overlay. So both of these, which I failed to mention, were unbonded overlays, and based on what I understand, that you may or may not have the ability to do bonding on this other roadway segment that you're looking at in Bolivia. So here's the first case that we spoke about earlier, that we have a 20 centimeter existing concrete pavement. It happens to have reinforcement in it. You can kind of see this old pavement here as they mill up the asphalt. and we want to go to an unbonded overlay with short panels. And we'll look at asphalt interlayer or geotextile as the separation between the old concrete and the new concrete. We'll design that with 20 million easels and for 20 years. And we want to use macrosynthetic fibers as the reinforcement there to help with our thickness design. So we're going to use a program we talked about yesterday. And that program was developed by Dr. Kazanovich for unbonded overlays of existing concrete pavements. So it allows you to have an inner layer of asphalt or fabric, and it allows you to design the thickness of the new overlay with understanding that you may have different types of inner layers. So this is the overlay design, and I've included that, which I'll actually do right now so you can see where I'm finding all these things. So in this overlay design, we've actually used this website where it's a cloud-based design program. I'll stick that there, and then we'll go back to the design program. And it's a mechanistic empirical design program, very similar to the AASHTO pavement ME. In fact, Professor Kazanovich is the one who wrote this, and he's the one who also did the concrete design and the AASHTO pavement ME. And the first couple things is we will have to pick a climate, and so we're designing this road near Illinois. Indianapolis is located very close to where I live, which is close to where the project is. We'll do this for a 20-year design life. This overlay design program calculates cracking as well as faulting. We will input the average daily truck traffic for this facility. We won't have any growth in trucks, just to make it simple. And we want to do a short slab design, so about 1.8 meters or 6 feet. We do have concrete shoulders for this design, and we will use about 4.2 megapascal flexural strength in the concrete. The existing slab is 20 centimeters, and we'll first look at asphalt interlayer. And these are some of the properties of the asphalt that I'll just leave the same. So that's all the inputs. This design assumes that the existing slab is separated with an asphalt layer, and then it's going to determine the required thickness to maintain low levels of faulting and low levels of cracking at the end of the design life. Low meaning less than 6 millimeters of faulting and less than 15% slab cracking. So once we hit submit, it's going to do all the calculations. This does a curling calculation, both temperature and moisture curling. So although it looks like a simple design program, it does all the mechanistic calculations that you would expect. It does both the fatigue and fault development based on erosion. And once it's done here, this is for asphalt interlayer. It approximately requires about 15 centimeters, slightly larger than 15 centimeters of a required overlay with plain concrete. Now you see there was no fibers here. So we had, if we go back to our case study problem here, we said we wanted fibers, right? And so so we had about a little bit more than 15. It's probably closer to 16 centimeters without fibers. So now we're going to design it with fibers. And to do with fibers, remember, we're going to take the residual strength, which is about 1 megapascal. That's what we're going to do for this overlay. We're going to add it to the existing concrete. And so I've done that. So I have about a little bit greater than 5 megapascal now is the concrete strength. I'm going to resubmit that for the design, and obviously that should reduce the thickness here below what it was in that previous run. we'll see what the answer is here. We had about 15.5 centimeters without fibers. So with fibers, we're going to have, we should have something slightly less than that if it works correctly. Yeah, so we have about 14 centimeters now with fibers with this program. And so we go back to our design, and I've actually ran these beforehand. So you see about 14 centimeters is the required thickness with fibers and with an asphalt inner layer, assuming the effective strength is somewhere around 5 megapascal. If we go to the geotextile layer, then we can also look at this and just select geotextile layer and then rerun this with fibers with the geotextile layer. And this is about at 20 million easels for the design life. So not small, but not a major roadway that we would see in Chicago area. This is near Springfield, Illinois, which is a city of 150,000. So the traffic there is not as large as we would expect in other locations. So the required thickness here is about 16 centimeters now with the fabric for this particular case. And that's what we have here, about 16 centimeters for these short slabs. So that kind of shows you with short slabs and fibers with two different inner layers what happens with this unbonded overlay. And if we wanted to see what would happen with the traditional joint spacing, so this includes curling, but remember curling goes up with slab size. So if we pick a larger slab size, let's say 4.5 meters by 4.5 meters, then we can see the effect of slab size on the thickness design. So we'll do that, and we'll keep the fibers in there. We should expect a much greater thickness because the stresses in the slab go up with slab length, the curling of the slab goes up with slab length, and therefore the required slab thickness should be much greater than it is. And we get something that's approaching 20 centimeters from the program, which is what I have here. And it turns out, I won't run this part of the program, but with the geotextile or the fabric, you get about 20 centimeters here for this design. So this kind of gives you an example. This particular project, which was built 5 years ago, actually never was designed. They ended up just using 15 centimeters. So although this program said it should be somewhere between 14 and 16, they used 15 at the time, just based on experience. There was no design program. And so it wasn't that far from what the design software is actually telling you. So that's one type of example. This particular program is primarily used for designing overlays on existing concrete roads. But I wanted to go back to this project we had seen in Chile, where there was a very large amount of traffic in the port facility, close to 200 million easels. So let's take a look at designing this with the same program, and we can kind of use some assumptions to use this program to get an idea of what general thickness trends we would have if we designed with this unbonded overlay with short slabs. And just a reminder, this is heavy truck traffic, so we expect the thickness, if we're 189 million easels, to be much higher than what I just did. And recall the asphalt for this road was not as in great condition, so definitely unbonded overlay makes a lot of sense. The panel sizes are close to the 1.8 meter that the program allows us to use. We'll use the 1.1 megapascal residual strength values and go ahead and try to design this with the same program now. So we go back here, and remember that we don't have an existing concrete, but we have an existing asphalt. This is in Chile, so we have to find a similar climate. I'm going to pick Las Vegas because it's dry, a lot of sunshine, um, and probably has the same curling levels that you would expect in Chile. Probably not exactly correct, but it's pretty close. So we use Las Vegas climate zone. We will do a 20-year design life. Since this has a lot more trucks, we'll use 30,000 daily trucks in both directions, which is a lot. We will use our 1.8 meter slab sizes, and we're going to have asphalt shoulders in this case. And we will start the design with 1 megapascal design, so we'll be about 5 megapascal as the effective thickness. We'll reduce the existing concrete, because this is actually asphalt, to 6. It's probably going to be less than that effectively, but we'll leave that there. Maybe we'll reduce the modulus down even too, because that won't be as stiff. And we'll just put an asphalt interlayer in there, because we know there's asphalt directly below the slab. And then we'll just see what the program says that the thickness should be. This should create us about 190 million easels, and we can then figure out what the required thickness is. So we get a thickness requirement here, and we're going to go back to what I originally calculated. Yeah, 19 centimeters with fibers. So that's what I just calculated with the program. And if we didn't want fibers, our effective strength, or our real strength, is only 4 megapascal. So we would have to come back here and change the strength without fibers here and resubmit the value. And this should give us a thicker slab. Note the original design for this that they used with OptiPave was around 23 centimeters. So it's not exactly like OptiPave, the exact same thickness, but it's pretty close to it. And I'm not sure what strength they used in OptiPave, so I'm just guessing or estimating. And now we have, without fibers, we have 8.5 centimeters, which gives us about 21 centimeters for this 6x6 slab. Is that correct? Yeah. It's about 21.5 centimeters here. So you can see fibers for this high volume. And in this particular case, you notice we haven't used dowels or anything yet. And this has a stabilized asphalt right below it. So I know the La Pólvora project did not use dowels. If you were to change this to, let's say, a traditional joint spacings, here, let's say 3.6 meter slabs, you see that the slab thickness goes up pretty dramatically without fibers, 29 centimeters if you're at basically a 3.6 meter slab length. If you use fibers in the traditional slab length, we can do that quick, and then that'll be our last one before we do an example from Bolivia. So if we wanted to use kind of longer slabs, 3.6 meters with fibers, we could do that design and see what kind of thickness we get. Now you could imagine doing your own designs mechanistically by calculating stress in a separate analysis program. In this case, you get about 10.4 inches. If you convert that to centimeters, 10.4 inches to centimeters gives us about 26. So we can now go back to our program here, and this is about 26 centimeters here with fibers, 3.6 meter slabs. So we've done two examples now, two extremes, one in kind of where I live, one in we kind of tricked the program to do a design down in Chile, even though it's not 100% the same, because this program treats that you have a stiffer concrete layer, but we can do some things to kind of fool it. And then the next step is when I meet with you here in a bit, we will maybe talk about running through a kind of a design scenario between La Paz and Oruro, and that should be another type of design with different traffic and different inputs. So look forward to doing that here in a second. Marcelo, you want to kind of walk through what's left?
Yes, Jeff, thank you very much. Well, we will have some more data available soon for the La Paz Oruro project. I will share them as soon as I have it, but I thank you so much for the presentation. It was quite nice. And well, after this conference, we will have only the questions for the participants.
Yes, thank you.
Le decía a Jeff que pronto vamos a tener alguna información adicional que nos interesaba tomar como ejemplo algún sector de la carretera La Paz Oruro y tendríamos las preguntas de los participantes.